Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight are three of our students who I will let say hi and introduce themselves. And we will start with Eli.
Hi, I'm Eli. I'm a physics and astronomy student at UMD.
Hi, I'm Allie. I'm a chemistry/biochemistry student at UMD.
Hi, I'm Lynn. I'm a physics and astronomy student at UMD.
All right, so tonight we have the next edition in our exploration series where we are going to take a deep dive look at space telescopes, which is pretty much my excuse to talk more about James Webb. Not even gonna lie, that's why I picked this topic. So as I get everything set up, as always, if you have any questions throughout the show tonight, you can leave them down in the comments. Eli will keep an eye on that for me and will let me know as questions come up. If we don't get to your questions right away, that's usually because there's a bit of a delay. We will make sure to take time at the end to answer any questions that we don't get to. And I apologize, my eye is watering right now. Okay, let's get into it. As I said, we are going to be looking at space telescopes. So to get started, I think it makes sense to talk about what is a telescope. Now, we have done an entire show on kind of beginners or introduction to telescopes, which was mainly focused or was solely focused on kind of backyard telescopes, ones that the general public could purchase and use for themselves. For this show, we are talking about professional research telescopes, and in that case, they're pretty much all reflecting telescopes that use a mirror at the back of the telescope. And really, the purpose of the telescope is to collect light, magnify it, and focus it onto an instrument. And that is usually a camera, something to look at spectra, and there can be other types of instruments as well, but those are the two main ones. And so here are a couple of different designs for what this could look like, but the biggest thing is you have a big mirror at the back. You can have some secondary mirrors as well to kind of bounce the light to wherever you need it to go to then send it to those instruments that you're going to use. Now, because telescopes are collecting light, they're essentially light buckets. And what that means is we want as big of a telescope as possible, because the bigger the telescope, the more light you can collect. And the more light you collect, that means the fainter objects in the universe you can see. And so we try and make telescopes as big as we can. Here is kind of a comparison of many different professional astronomical telescopes that are either have been in use or are in use, or some of these exceptionally large ones are ones that are planned but haven't been built yet, but very excited for. All right, so telescopes, again, big light buckets. The more light you can collect, the fainter objects you can see. And this is particularly important if we're wanting to study things that are very far away, because the further away something is, generally, the fainter it is and the harder to see it is. One of the reasons we want to look at things that are very far away is because in astronomy, when we're looking at things very far away, you're technically looking into the past. And that's because light takes time to travel. So when you're looking up at the moon at night and you see the sunlight reflecting off of the surface of the moon, technically you're seeing light that bounced off the surface of the moon a little over a second ago. So that light you're seeing took 1 second to travel from the moon to us. If you're looking at the sun in the daytime sky, that light takes about 8 minutes. So looking at the sun, you're seeing it as it was 8 minutes ago. Now, if we go even further out, like say, let's jump all the way out of our galaxy to the next galaxy, the Andromeda galaxy. The light that we receive from the Andromeda galaxy took 2.5 million years to get to us. So we're seeing it as it was 2.5 million years ago. So if we want to look at the first galaxies to have formed, we need to look at objects that are 13 billion light years away, because that light took 13 billion years to reach us, and therefore we're seeing that object as it was 13 billion years ago. So this is why we want really big telescopes to collect as much light as possible so that we can see very far away and take a look at these very distant early universe objects. Now, for the most part, our observatories are on the ground, and that's because we have all of the resources here. It's a lot easier to build something very big here on the Earth than to build something very big up in space. And so all of the major observatories, or most of the major observatories, are on the ground. But there are problems with that. Because the population on the Earth is growing and spreading, cities are getting bigger and bigger, light pollution is becoming more and more of a problem, so we don't have as many good dark sites to do astronomical research from. So things like light pollution are making it harder and harder to do astronomy with telescopes here on the ground. Another problem we have by doing astronomy here on the ground is our atmosphere, which of course we absolutely have to have for our survival. But because that atmosphere is always in motion, it bounces the light around that's coming from objects in space, and that can make the object look blurry. And it hinders how good of a picture we can get of this object. So our atmosphere can also make it difficult. And this is one reason why, even though we could build really big telescopes here on the ground, for a while we didn't, because it didn't matter. Because our atmosphere didn't make those big telescopes any better than some of the smaller ones. Now we've got technology to kind of address this, and it's a separate topic. I'm not going to get into it. But that is something that we have to deal with here on the Earth. The third problem that we have to deal with from here on the ground is the fact that our atmosphere doesn't let all types of light through, which is a good thing for us. Our atmosphere stops things like gamma rays and X-rays and most UV, most ultraviolet light. These are very energetic light that are incredibly dangerous, especially at high levels. So it's a very good thing that our atmosphere blocks those. However, that means we can't study that light from here on the Earth. Same with infrared. Most of the infrared and some of the microwave section of light also gets stopped up in the atmosphere and doesn't make it down to the ground. Really, the only things that we can study from here on the ground are visible light and radio. Anything else we would need to get outside of our atmosphere to be able to study, and that's where the space telescopes come in. They allow us to get away from light pollution. They allow us to get away from the blurring effects of our atmosphere, and they allow us to study types of light that don't make it down to the ground. And the reason we want to study all of these different types of light is because they show us different things. So what you're seeing here is a picture of the Whirlpool Galaxy, but it's taken in different types of light. And so you can see here how these different types of light highlight different features and show us different things within the galaxy. So for example, radio is going to show us where all of the cool gas is, and that tends to be where star formation is taking place. And X-ray light and gamma rays are going to show us where all of the hot gas is. And so we can see, again, different elements, different things with the different types of light, and that's why we want to look at it. In some cases, looking at different types of light can even show us things that we can't see in visible light. And this is one of my favorite examples of this. This is the Crab Nebula. In visible light, it looks like this. This is the Hubble image. Absolutely beautiful, love it. But there at the very center, in X-ray light, sits this disk and jet from the pulsar that's at the center of the Crab Nebula. And this feature you don't see in visible light at all. So these different types of light can actually show us features that are completely unseen in other types of light. Also, this is just a stunning image. I love it. Okay, so to build a space telescope and to use it to study all of these different types of light, there are actually a few different designs that you have to have, depending on which type of light you want to look at. Now, for a space telescope to study visible light, which is the light that we see with our eyes, UV light or infrared light, you actually have your classic reflecting telescope design, just like the reflecting telescopes that we use down here on Earth. They act exactly the same. The one difference you can have, though, is if you're looking at infrared, you have to keep the telescope very, very, very cold. Because infrared, another way of thinking about it is heat. Anything that's hot gives off infrared light. So if the telescope itself is warm, it'll glow in infrared, which will interfere with us trying to see the universe in infrared, because the telescope itself is going to glow. So that's the only difference, is infrared you have to keep everything very cold so that you don't interfere with that signal. Now when it comes to more energetic light, like X-rays, this is when we start having to get into a very different type of design for the telescope. Because X-rays are so energetic, they don't bounce, they don't reflect like visible light waves do, like visible light does. So instead of having a curved mirror at the back of the telescope, what you end up doing is having these kind of nested concentric cylinders of mirrors, so that when the X-rays come in, they barely graze the mirror, which very slowly focuses it back to a detector. So it's just a same, still using mirrors, it's just in a different configuration to account for X-rays being a lot more energetic and therefore harder to kind of control and focus to a camera or a detector. Now going even higher into gamma rays, those don't bounce at all. Gamma rays just go through everything. So you don't have a conventional telescope for a gamma ray telescope. It's more of a series of detectors that can detect as the gamma ray comes through. And by having the different series of detectors, that allows you to trace the path that the gamma ray took through the detector, and that can then give us a path to trace back to try and figure out where the gamma ray came from. So it's not, you're not doing imaging like you technically would in like visible light or infrared or UV. It's more of you're detecting a gamma ray and you're kind of backtracking its path to try and figure out where it came from. It's very difficult work to study gamma rays. All right, so these are our kind of basic designs for telescopes in space and why we want to put them there. So let's start taking a look at the kind of history of how we started getting these telescopes up into space. I actually had a lot of fun looking into this, and it turns out the first kind of record that I found of serious talks about putting a telescope somewhere other than the surface of the Earth actually was in 1837, which is a conversation, it was a discussion between these two gentlemen, Wilhelm Beer and Johann Madler, I think is how you say his name. These are both German astronomers. who were discussing the advantages of putting a telescope on the moon. And that's again, kind of the first major record I saw of like a serious discussion of telescopes elsewhere other than the Earth. Now, the kind of start to the actual space telescope program got its start in 1946, thanks to Lyman Spitzer here, who wrote a paper proposing the benefits of putting a telescope into space. And it was actually that kind of launched the discussion and the eventual placement of telescopes into space. So the first attempt was made by NASA with the Orbiting Astronomical Observatory, or the OAO. Now, OAO-1 launched on April 8th, 1966. It was had instruments to detect both UV, X-rays, and gamma rays, which again, those are what we can't see from here on Earth, so it makes sense that those were kind of the first types of detectors, the first types of telescopes to put up into space. Unfortunately, OAO-1 was not successful. It had a power failure about 3 days after it launched and never ended up working. So that was the first attempt. The second attempt, oops, I forgot I have them all on the same slide. The second attempt was OAO-2, which consisted of 11 UV telescopes. It launched on December 7th, 1968, and it was successful. It was the first successful space telescope that we put into orbit. And it observed until January of 1973. So it spent quite a few years up there. Some of its most notable discoveries were that comets are surrounded by these hot hydrogen halos, and also looking at the UV light coming from nova bursts. So that was our very first. Now, the OAO program had 2 other missions, OAO-B, which was also unsuccessful, but it failed kind of almost immediately because it didn't detach from the rocket. So it all got just pulled back down to Earth and destroyed. But then the fourth attempt, OAO-3, was also successful. It launched on August 21st, 1972, and operated until February of 1981. So those were kind of the first. Now, around that same time, the Soviet Union was also working on putting telescopes into space, although they had a slightly different tactic. Their first successful attempt was Orion-1, which they installed on their space station in June of 1971. So instead of putting a telescope just in orbit around the Earth, they sent it to their space station and attached it to that. During that time that the telescope was up there, it was operated by Viktor Pastiev. I'm probably saying that completely wrong. But he holds the title of being the first man to operate a telescope outside of Earth's atmosphere. And then their second Orion telescope, Orion-2, instead of being attached to the space station, just went up in one of their spacecraft. And so it went up, stayed up for, I think it was just a few orbits, and then came back down with the space station. And that was in December of 1973. All right, so those were our first attempts. Now, back when Lyman Spitzer was making his argument for putting telescopes into space, what that conversation ended up prompting was the program that eventually became the Hubble Space Telescope. So after Spitzer's, trying to go back and find the date real quick. After his paper that he wrote back in 1946, that prompted the discussion of this, which eventually led to funding being granted to the project in the 1970s, and the Hubble Space Telescope was made. So it has a 2.4 meter mirror. It has 5 instruments, and it is capable of observing UV, visible, and near-infrared light. It launched in 1990. However, right after it launched, there was a little bit of problem when it turned out that the primary mirror in the telescope was actually ground incorrectly. So it was not focusing the light. They ended up sending a service mission up in 1993 that added some lenses, basically like a pair of glasses, to the Hubble Space Telescope to account for that, and that allowed it to focus and work properly. What was really interesting with Hubble is it was the first telescope, and I think the only space telescope that was designed to be accessible by mission so that it could be maintained over the years. And that was really crucial, especially given the error in its mirror right at the start. It's a very good thing that it was designed to be serviced. So it's been up since 1990, and it is expected to last all the way through anywhere from 2030 to 2040. It's going to have, we're looking at 32 years this year that it's been up there, and we've got maybe another decade left for it. So, which is very cool. Hubble's been doing amazing stuff, and of course, it showed us so much about the universe. Just being able to see things at much better precision, much better resolution than we can get here on Earth, because it's not having to deal with our atmosphere. And it's just, you've seen all the gorgeous images. I would say one of the most notable is probably this, which is also my background. This is the Hubble Deep Field. I think this one actually in particular is the Hubble Ultra Deep Field, which is a patch of the sky that is smaller than your thumbnail held out at arm's length. And it just sat staring at this patch of sky for hundreds of hours. And that patch of sky, to us, to our eye, looks like there's nothing there. But when you look at it for hundreds and hundreds of hours, you actually see that there are hundreds of thousands of galaxies just within that tiny little patch of sky, which really expanded the, not density, it showed how much stuff there really is in our universe, how many galaxies there truly are. And this is just a stunning image. I love it. All right, so Hubble, launching in 1990, was the first of what NASA has called their 4 great observatories. The second to launch was the Compton Gamma Ray Observatory. It launched in 1991. And then was decommissioned in June of 2000 because of a gyroscope failure that happened in December of 1999. So this one is no longer operational, but it was a gamma ray observatory, so it looked at gamma rays. And this is one of the things that it did. This is a gamma ray map of our galaxy. The third great observatory was the Chandra X-ray Observatory. This launched in July of 1999 and is still operational. And it goes, of course, as I said, is an X-ray telescope. And these are some of the just stunning images. Now keep in mind, since this is X-ray, this is not what it would look like to our eye because our eyes can't see X-ray light. What we do is we create false color images by assigning colors to X-ray. And that's how we end up getting these really cool pictures. And then the fourth, and Chandra is still operational. I don't know if I mentioned that. And then the fourth of the 4 great observatories was the Spitzer Space Telescope. This one was an infrared telescope that launched in 2003. This was a really big deal because Spitzer was the first telescope to be put in orbit around the sun and not in orbit around the Earth. it was actually in an Earth trailing orbit. So it orbited the sun, kind of following along behind the Earth, and it was the first telescope that we did that with. But this was important because it's an infrared telescope. We want it to be far away from the Earth, which gives off a lot of infrared light. So this mission, again, it launched in 2003, and it ran until 2020. So back in 2009, it actually ran out of the liquid helium, which was helping to keep it cool. But one of its instruments was still able to work even at the warmer temperatures. And so most of the instruments went offline in 2009. That one instrument continued to run until 2020, where it was turned off. The whole telescope was turned off because it ran out of fuel, I believe. And so Spitzer is no longer operational because it has run out of fuel. So those are the 4 great observatories. There are 2, well, really 3 others that I want to mention that are very important to kind of astronomy and to space telescope world. The first is, oh, sorry, I forgot. I found some beautiful images from Spitzer. This, again, these are false colors. This is not how it would look to your eye because we're looking at infrared light, which our eyes can't see. So the other one, or one of the other ones I want to talk about very quickly is COBE, the Cosmic Background Explorer, which was launched in 1989 to study the cosmic microwave background, which is the remnant heat from the Big Bang. And its results pretty much confirmed the models that we had of the early universe and Big Bang, or at least a lot of the major points in the model. So this was a huge win for cosmology. And then, of course, we also have the Kepler Space Telescope, which launched in 2009. It also was in an Earth-trailing orbit, just like Spitzer. But this has been absolutely instrumental in finding planets around other stars, because that's what Kepler did. It stared at a patch of sky, took measurements of those stars every 30 minutes, sent that data back to us, and helped us look for planets around other stars. So it ended up running for about 9.5 years. Over its time that it was operational, it observed 530,506 stars and found nearly 3,000 planets around other stars, among other things that it also found. So Kepler has been just super important and is no longer active. It got shut down in 2018 because it ran out of fuel. And then, of course, all of this leads up to the next great space observatory that just launched and is in orbit, and we're so excited, and that is the James Webb Space Telescope. Now, this was very big. I mean that literally and figuratively, because this is the largest telescope that we have launched. And because it's so big, you couldn't fit it as it was into the spacecraft to launch it. It had to be folded up. And this is the first time we've attempted this sort of thing. But it works. It got up there, it unfolded, it is now in its orbit, which is kind of to the side of the Earth in what we call L2, or Lagrange point 2. It successfully is in orbit. Now we're just waiting for it to cool down and start taking images. We're expecting the first flight to be in about 5 months, which is very exciting. Now, because James Webb is much larger than Hubble, it's going to be able to see things that are a lot fainter than Hubble could. But it's also looking at a different type of light. James Webb is looking at infrared light to see those objects that are at the very beginnings of the universe, with the idea being that James Webb is going to look at the very first stars and galaxies to have formed. And we are ecstatic about this. All right, I know I'm out of time, so just very quickly, this is not kind of the end. We have lots of future space telescopes planned. The two that I thought were the most exciting are LISA, which is the Laser Interferometer Space Antenna. It's basically 3 spacecraft in a kind of triangle configuration that are bouncing lasers between each other. And by measuring the distance between the spacecraft, we can detect if gravitational waves are moving through. So this is going to be very important to gravitational wave astronomy. And then the next, that's really cool, is the Large Ultraviolet Optical Infrared Surveyor, which is, while James Webb is the kind of spiritual successor to Hubble, because it's not looking at the same type of light, this is meant to be kind of Hubble's better replacement, because it's going to look at the same type of light that Hubble does, but it's going to be much, much bigger. How much bigger, we don't quite know yet. There are 2 designs that they're debating between, either this 8-meter or this 15-meter. But now with the success of James Webb, this is making this new telescope seem much more likely, because it's going to have to rely on the same sort of origami kind of folding and unfolding to get up there like James Webb did. But yeah, they're looking at a gigantic possible future space telescope to be Hubble's grandchild, we'll say. I don't know if it would be a child, but anyway. I think I've babbled on about space telescopes enough. There was so much to talk about in this. But hopefully now you have a good early start to an understanding of why we put telescopes in space, what type of things we look at, how we look at it, and some of the major telescopes that have been put. Those were only like a handful. There are so many more that have been up and are still currently up. So yeah, that is exploring space telescopes. Now, if you have a topic that you would like for us to do in the next exploration show, make sure you let us know, because we of course want to do these to cover topics that you are interested in. All right, let me bring us back over. And let's see if we have any questions.
Yes, we got a couple. First one, hello students, although the topic is space telescopes, what are your observing experiences? I can go first. So I've done amateur observing on my own. I've done a lot of observing with the Planetarium for public programming and things like that. Mostly looking at intersolar system objects like planets, although I've seen some other objects. Aside from that, for one of the classes in the astronomy curriculum at UMD, we used ground-based observatories to order images so that we could do projects. I don't know how you describe it, Jessica. Jessica taught me that class.
Yeah, I mean, it was simple observational astronomy projects that could be done with small ground-based observatories.
Yeah, yep. And then aside from that, I have used, I mean, not observation that I've done, but relative to space telescopes. My research has heavily depended on space-based telescope images, optical images of galaxies. So, gotten some.
And some you're starting to get, or you were starting to get into X-ray.
Yep, starting to get into X-ray too. But that's kind of on the back burner for now. So, yep.
I don't know, Lynn or Allie, if either of you have any observing experience.
I don't have any experience with anything super fancy, but when my grandpa passed away, my family inherited his really old telescope, and it's really old. It's probably between like 50 and 60 years old, in fact, but it actually is really great for looking at the moon. So when the moon is really bright, we can even see the craters, and it's very pretty. So you can definitely make use of what you have at home. I even know that a lot of people will, like, if it's dark enough, use binoculars too.
Yep.
So you just kind of have to make do with what you have, but it's still really awesome even looking at the moon.
Yeah, absolutely. Like, it's crazy. It's really funny watching people look at the moon through a telescope for the first time. Because everyone thinks they know what the moon looks like, right? And then you see it close up for the first time, and it's a magical moment. And that's one of my favorite things at like the star parties and stuff that we do, is just getting to see people seeing things for the first time. Like, I love it.
Yeah, there's something really special about seeing it with your own eyes. Like everyone's seen like the Apollo 11 pictures and the like really detailed pictures of the moon, but it's really special when you get to see it yourself.
Absolutely.
Len, do you have any observing experience?
I don't really have very much besides just like the basic, going somewhere really dark and looking at stars and stuff. But I really, in the future, I want to get into observational astronomy a bit more and, go places where there's a lot less light pollution where I can try to see more things.
Well, I'm assuming you'll be taking observational astronomy class next year.
Yeah, you have to.
I mean, yeah, if you're doing an astronomy minor, you're gonna have to take my class.
Yeah, I look forward to it. I definitely plan on it. I just haven't been able to fit it into my schedule yet.
And then another question, okay, physics students, visible light is centered at green, which is the middle of the rainbow, which if I recall correctly has a photon energy of on the order of 2.38 electron volts. The forward voltage drop of a green LED is a bit above this, about 2.7 volts. What temperature is such light? Len, I don't know if you want to take a stab at that.
Well, I don't know any of that off the top of my head, but I have done problems with that in the past.
Isn't it about 5,700 Kelvin?
No, so I scratched it out really quick. And if by the temperature of that, you mean the temperature a black body would have to be to emit that color light, it would be somewhere around 4,700 Kelvin, which is around 8,000 Fahrenheit. So, yeah, but we can't, we don't have stars in that range. So I didn't know that one off the top of my head. Like red, like the sun, is like 5,700 somewhere around there.
Well, the sun, it's yellow green.
Yeah, right.
Yeah.
But like that color is like, what is it, like 5750, somewhere around there?
Yeah.
Does the University of Minnesota Duluth have an observatory? Not yet.
Not yet. We're working on it. We are trying so hard to get an observatory. It used to, and then I think it got taken down for, I think there was just repair issues and it wasn't getting used. So it was taken down, but we are desperately trying to get one back. So hopefully. All right. Well, I think that's the last of our questions. I'll take one more short call for any questions while I do a little bit of just kind of promo for what's coming up over the next week. So next week is the beginning of February. So we will be doing next Wednesday our What's Up show, which is going to take a look at the astronomical events coming up in February. And then next Saturday will be our February constellation show, looking at the stars and constellations that you can see up in the sky during the month of February. All right. Yeah, I think we're good. Not seeing any other questions. So thank you everyone so much for joining us tonight. If you liked that and want to see more of our stuff, we have about 2 years worth of streams that we have done saved on our Facebook page in the videos tab or on our YouTube channel, which is linked in the video description. We are also still regularly streaming every Wednesday and Saturday at 7 p.m. Central and plan to do so for at least another month. We're hoping for some fun changes in March, but I'm not going to say too much because last time I did, we ended up not doing it because everything is crazy and up in the air right now. But at least through February, we'll continue streaming at this regular schedule. So again, thank you everyone for coming. Have a wonderful rest of your weekend, and we will see you again next time. Bye, everyone.